All right, so in this video we want to look at proving this theorem, which is a very important theorem, the fundamental theorem for line integrals, which says let R be a region in R2 or R3 and let phi be a differentiable potential function. So what does potential function mean? It means that the gradient of this phi is some vector field. So if F is that vector field that is the gradient of phi, which in turn would mean that F is conservative, so we have to have F conservative here. Otherwise, this nice, beautiful little shortcut won't work. Then the line integral of f dot t ds is equal to, and this is just another notation for this same line integral using the variable r instead of t with all those substitutions. We can find that value by simply taking phi of b minus phi of a, where b would be the point equivalent to your starting spot or your ending spot, and a would be the point equivalent to your ending spot. So let's just think about what that b and a are for a second. So let's say we've got this, and we've got some curve C. Okay, so that's this guy here. And if we want to evaluate this line integral, say from t equals, let's call it a, t equals little a. Let's just take that out. T equals little a to t equals little b. So when I'm setting up, say, this line integral here, if I'm doing everything in terms of t, so remember we did r of t dot r prime of t dt, and I had everything in terms of t. So I would be going from some t equals a to some t equals b. So this big A and this big B are not these little a and little b. Big A and big B are points on the curve. Little a and little b are the values of the parameter. So let's say this point right here at t equals a, I don't know, we'll call it x sub a, y sub a. I'm going to call this point right here point A. All right, and this point right here, let's say it's some x sub b, y sub b. I'm going to call this point B. So basically what we're saying then is if we know that f is conservative and we know that phi is the potential function for f, then all we have to do to find this line integral is plug a, let's start with b, plug b into phi and plug a into phi and subtract them. So we could also write this, say, as like x sub little b, y sub little b. We're going to plug those values into phi because remember phi is some function of x and y. So we're going to have to plug in some values of x and y. Okay, so that's how big B and big A correspond to like t equal little a and t equal little b. Hopefully that helps. Okay, so this is what we're trying to prove. So notice this is just an if-then statement that we're proving. If, then. So this is the stuff we know. This is what we know. We're going to start with that, and then we want to be able to prove this relationship is true. All right, let's give it a whirl. So let's start with what we are given. Okay, so we're given that f is conservative. I'll skip that part and just say equal to the gradient of phi. So let's say phi is some function of x and y. And let's define c for our curve to be some r of t, which we're going to write as, some the x component as a function of t and some y component as a function of t. So this is all set up. So if I take this curve, some point on this curve, this r of t, and I want to plug these points into my phi value, I could say, let's think about phi of x of t, y of t. Now, do you remember, how to take the derivative of that? Well, we're going to have to use the chain rule, okay? So if we take the derivative, not the partial, but the straight up derivative of phi with respect to t, that's going to equal the partial of phi with respect to x times the partial of x with respect to t plus the partial of phi with respect to y, oh, those look like 2's, times the partial of phi with respect to, or y, excuse me, partial of y with respect to t. Partial y, partial t. Remember that chain rule? It's been a while since we've done that. Back in chapter 14, I think. Alrighty, so now what we want to do now is write this as the dot product of two vectors. Can you do that? Dot product of two vectors. It looks like it's kind of set up for that. Do you see it? Alright, so this is going to be partial phi, partial x, comma, partial phi, partial y, dotted with partial x, partial t, partial y, partial t. All right, see that dot product? Okay, that's kind of interesting. Now, how could I rewrite this? So this is the derivative of phi with respect to t. What does this look like? What is that? Partial phi, partial x, partial phi, partial y. Yeah, that's the gradient, isn't it? That is the definition of the gradient of phi. And we're going to dot that with, okay, what does this look like? What is this? Compare it to what's happening up here. If r of t is x of t, y of t, what is partial x, partial t, partial y, partial t? Well, that's going to be r prime of t. Now I know those are partial derivatives, but that would be the same thing, right? If this is all a function of t, then, you know, if you take the partial with respect to t, it's going to be the same thing as the derivative with respect to t if there's only t's there. Okay, so this is some good work. We're going to leave this here. We're going to come back to this. We're going to use this. This is going to be nice, this little relationship here. So let's just put a pin in this nice relationship, and we're going to come back to it. Now, we're trying to prove something about what this is equal to, what this line integral is equal to. We want it to come out to be that. So we're going to start messing around with this line integral here and see if we can make it come out to be this. All right, so I'll just start with, I'll start with this guy right here, which is equal to that. And then we're going to rewrite it in terms of t. So we have the line integral of f dot dr, and we know that can be rewritten out sort of the long way as f evaluated at r dotted with r prime of t dt. And actually we can put in our, now that we've got the t's in there, we can say from a to b, because that's going to be from t equals a to t equals b. It doesn't make sense to put the a and b in here because those are values of t and there's no t's here, so we just put c. All right. Well, we know that f is equal to the gradient of phi, because that's given. F is conservative, and we said that phi was the potential function. So instead of f here, I'm going to write gradient of phi evaluated at r of t dot r prime of t dt. So now let's take a look at what we have up here, this work we did. We have gradient of phi dot r prime of t, and this is the derivative with respect to t, so this would all be in terms of t as well. Okay, so this is all in terms of t. So all this stuff here is equivalent to the derivative of phi with respect to t, right? Well, now this looks like a pretty easy integral to think about, hopefully. This function right here, maybe I'll write it in a different color. Let me write it in a different color. Let's write it in green. d phi dt. So if I want to take the integral of the derivative of phi with respect to t, if I want to take the integral with respect to t, that's just undoing itself, right? That's the antiderivative. What is the antiderivative? That's just going to be phi. And by the fundamental theorem of calculus, that says, you know, take phi of t and evaluate it from t equals a to t equals b. Well, another way of saying this then would be to take phi of xy and just evaluate that from, instead of t equals a, t equals b, we're just going to look at this point, capital B and capital A. So what is the point when t equals a? That's capital A. What is the point when t equals b? That's capital B. Or you could just use the little subscripts, but this, to get it to come out to what the theorem says, we'll use capital A and capital B. So that's just phi of b minus phi of a. Okay, and we have it. So we've showed that this integral was equal to this right here. And the interesting thing to really realize is this is all relying on the fundamental theorem of calculus. It really all boils down to that. And we just had to do a little work up here to show that all of this stuff right here that's in this line integral is really just equivalent to the derivative of phi with respect to t. All right, well, I hope that helps.